Okay, time to get started. This press conference is about our tornadoes getting stronger, and our speaker is James Elsner. He's with the Department of Geography at Florida State University in Tallahassee, and he just came fresh from giving the Gilbert White Lecture, which is a special lecture of the Natural Hazards Focus Group. He's here just from having delivered that lecture on the same topic.
Okay, thank you very much, and welcome everyone. Okay, so the title is necessarily provocative, and the reason is that I think that it's time for us to start thinking about the question about how these severe local storms might be affected by climate change. And so if you go back about 30 years, and you talk to the hurricane folks, they would have kind of rolled their eyes if you said there was a connection between hurricanes and climate, right? And so there were the climate folks doing the large-scale stuff, and then there were the hurricane specialists. And they really didn't communicate. They didn't really talk. Now, of course, we know that how hurricanes are affected by climate to some extent. We make seasonal forecasts, and so we can start addressing these questions. And they're very important questions for society. And I think if we move forward to today, I think we're in the same place we were 30 years ago with tornadoes and severe local storms. I think there's a lot of folks out there who just don't want to even think about the question. We go down even another scale. We're on a much smaller scale with these severe local storms. And I thought that there may be some relationship to the climate is usually just scoffed at. And so, again, necessarily provocative. But I think what I'd like to show is some evidence that, in fact, this is an important topic, and there is some evidence that tornadoes are getting stronger. So this is work I'm doing at Florida State University, and so we start with a problem. The problem is that the damage scale, the way we rate these tornadoes, their intensity is categorical. That is a discrete categorical, it's ordered categorical data. But if we want to estimate how strong a tornado can get, that's going to require a different kind of scale. It's going to require a continuous intensity scale. So for example, we can count the number of tornadoes by EF rating, and we can even focus on the strongest tornadoes, the violent EF4s and EF5s. But if we look at a time series of the number of tornadoes by EF rating, that doesn't answer the question, are tornadoes getting stronger? So again, just as we did it with the hurricane problem, we're going to think about the tornado problems frequency separate from intensity. And that makes sense because the processes that make a season active in terms of tornadoes may not be the same processes that intensify a particular tornado. So, so you hear people say, well, if we just look at EF4s and 5s, we don't see an upward trend. Well, yeah, but that could be because there are more tornadoes in Canada. There could be fewer but stronger. So we want to try to address these questions. If we can solve the problem of a categorical intensity scale, make it numeric, then we can get plots like this, showing the tornado wind speed in meters per second on the vertical axis as a function of year on the horizontal. And so we can see that the tornado intensity appears to be going up. Okay, now I want to caution you that these are preliminary results, and I'm not trying to say that this is the climate footprint on tornadoes. That's not what I'm about here. What I'm saying is we have the tools, we have the data to start answering these questions. Okay? And so I think it's important to make that distinction. I think it's provocative, I think it's newsworthy, but it's not necessarily the next hockey stick. So what are tornadoes? Okay, so these are these violent microscale wind systems that form from thunderstorms. They come in all shapes and sizes, and so they produce all shapes and sizes of damage paths. So that's what you're going to hear throughout here is this idea of a damage path. So how do tornadoes form? Well, they need two ingredients. They need the available potential energy, that's the warm, moist air from the Gulf of Mexico, and they also need cool, dry air coming from the Rocky Mountains. And the key ingredient here is that the key concept here is that the air that's rising, producing the updraft, is separate from the downdraft. So where I come from in Florida, we get thunderstorms all the time, but we don't get tornadoes as often because the air that's going up starts to precipitate, and that kills the updraft. whereas these supercell, as they're called, thunderstorms, are rotating, and the updraft is separate from the downdraft. We need one other ingredient to get the tornado to form. So we got this rolling motion of the air coming into the updraft. It gets tilted into the vertical. That starts the air spinning. But the strongest spin is actually going to be at the cloud base. If you think about rolling that spin up, it's going to be the fastest at the cloud base. So how do we get the wind to blow fast at the ground? We got to have air coming in at mid-levels, wrapping it back around and kicking it up near the ground. So we know these things. We know about how tornadoes form. So when a tornado occurs, it produces a swath of damage. And so this is the damage path. This is different than the debris path. This is the actual where damage was recorded. So this is an example from Moore, Oklahoma, just a few months ago in May. We were in Oklahoma City at the time, and this was the tornado that occurred. Produced lots of damage, and this is the outline of the damage path in gray. Okay, so that's the outer contour of the damage path. Inside, in the gray areas where there was damage found, outside there was no damage. So we could take the damage path, and we can think of two characteristics to describe it. We can think of how long it is, and we can think of how wide it is. Now, width is going to be measured as, in meters, as the widest distance, transverse to the length of the path. And length is just from the touchdown point to the point at which it goes back into the cloud. And so it turns out that if we look at length and width, and this is recorded in the Storm Prediction Center's data set, if we look at length and width for these tornadoes, there's a very nice relationship with the EF damage category. Okay, it's not one-to-one. You can't, given tornadoes, length and width is not going to predict the damage exactly, but on average, it does a really good job. You can see in panel A there that the stronger Category 5 tornadoes tend to be longer, and so on. There's actually a very nice relationship. Same with width, the upper right panel. You do it in 2 dimensions there in the lower panel. Again, length on the horizontal, width on the vertical, and then the dots color-coded by F scale. You can see that the strongest tornadoes are up in the upper right-hand corner. Okay, so it's a very nice relationship, and as a statistician, statisticians drool when they see stuff like this. This is really a remarkable kind of result. And so, in fact, we can table this. So this is just facts from the data since 1994 to 2011. There's your category, EF1 through EF5, the number of storms in each of the categories, the mean length, the median length, the mean width, the median width. You can see a very, very nice statistical relationship. Okay, so, and I'm using 1994 because that's when the U.S. had almost complete covered by the NOAA's WSR 88D data. Now, the Doppler radar data doesn't, if there's a tornado vortex signature on radar, they don't put that tornado in the data set. They have to go out and verify that there was actually damage done, that it was caused by a tornado. But at least they have a way to say, maybe let's go look for some damage, if none was reported. So that's kind of so here's the punchline in terms of the statistic. It basically says, I can think of the probability, given my length and width, I can assign a probability for each of the damage categories. So if it's a long tornado and a wide tornado, the probability that's an EF5 is high, and the probability that's an EF1 is low. If it's a short and narrow tornado, the probability that's an EF1 is high. Probability that's an EF4 is practically zero. So what I can do is think about this probability distribution, a number for each EF scale category given the length and the width. L is length, W is width, and it's just a cumulative logistic regression. Okay? So it's nothing really complicated, but it allows us to work with these ordinal categorical data and length and width and ascribe a probability distribution. Now, once I have that probability distribution, so I have the length and the width, I have a probability that the storm was in each of these categories. Then I can multiply the characteristic wind speed for that category. So each category has a lower bound and an upper bound. Take the characteristic value, either the median or the mean. That represents a characteristic wind speed. Multiply that wind speed by that probability. So it's just like a weighted average. If it had a lot of probability in the weaker categories, then those wind speeds will be weighted more. And so I turn a categorical scale into a continuous scale in this statistical way. And so now I can make some progress in understanding. But we understand that there's more to it than that. And there's issues with these data. One of the major issues is what we call the population bias. And a population bias is a jargon term to say that we're more likely to observe a tornado if it occurred near a city or a town. So this graph basically verifies that in the data, that if you're near a city at distance 0, your tornado report density in, let's say, 10 square kilometers is higher than if you're farther away from the city. And there's a nice relationship that we can quantify. Moreover, that population bias is decreasing over time. So I think about that as a snake plot. And the upper left corner then is just the data from the 61 through 70. The lower right then is the last decade, 2002 through 2011. So as you would read them across, we get later in time, and you can see that what happens to that snake plot, right? First of all, you see that it goes up and down. Well, that depends on how active the season was in terms of the tornado. But more importantly, you see the snake starting to fly flat. Okay? The year of the snake, right? It's starting to lie flat. That indicates that the population bias is decreasing with time. And that's in the data set. It's a very nice result. It's what you'd expect. Okay? And so if someone's going to correct the data or make some adjustments for the data, they have to understand that that adjustment has to be a function of year or time, right? But we put that into the model. So we get our wind speeds. This is the figure that shows us predicted wind speeds here on the horizontal axis and the frequency. So this is Category 1 storms. So if our model was perfect, all of these histograms would be orange. All of these would be green. All of these would be blue. All of these would be purple. And all of these would be gray. So we're not perfect, right? In fact, we're under-dispersed, especially at the lower scale. But we generally capture the essence. The wind speeds correspond to what we might expect from the data. That's based on the model. And in fact, if you look at the range of wind speeds in each of the damage categories, let's say the first category from about 33 meters per second to about 50 meters per second, you double that for miles per hour roughly. You can see that's in red. And you can see our model's in black. So our prediction is actually narrower than the EF range. So that tells you there's useful information on length and width to tell you where the intensity is on that storm. So we tried to look at some data that wasn't used in the model to build the model. These were some tornadoes from this year, 2013. And you can see these were estimated based on damage winds. This is what our model predicted. Okay. It's a small sample, just a few tornadoes. But we also looked at a set of historical data from the Doppler on wheels. You're probably familiar with this project. It's a very well-publicized project by the National Science Foundation to go out and drive these Doppler trucks into the tornadoes or in the vicinity of tornadoes and get data on wind speed. So these wind speeds from 12 tornadoes are independent of the damage, completely independent. They're just based on radar estimates. And we correlate those with our modeled estimates, and the correlation is 0.82. Again, small sample size, but it's a reasonable model. And the range of wind speeds for those tornadoes was between 38 and 91 meters per second. Okay, so we see that our model is able to take a categorical scale, make it a continuous scale in terms of meters per second, which is wind speed, the idea of the fastest rotational wind speed. We can also then think that on this scale, there's a balance between the centrifugal force, the force that wants to push the winds out, and the pressure gradient force. And that balance results in kinetic energy that is velocity squared divided by 2. So you can think of this as the kinetic energy, or the mass-specific kinetic energy, if you will, of the tornado. So I have velocity now. I can't do this with the EF scale, but I can do it with my velocities. I can look at the kinetic energies. So here's my kinetic energy, my mass-specific kinetic energy for every tornado since 1994, plotted by year, vertically by year. Okay? And you can see that there tends to be a trend toward more larger kinetic energy. So the bottom blue line is the 50th quantile regression. The 75th quantile is the next blue line, and the 90th quantile intensity is the top blue line. So the mass-specific kinetic energy trends are upward over this 18-year period. Again, I'm not claiming that this is a footprint of climate change. What I'm claiming is this is the way to start to answer those questions. Okay? More work has to be done. Finally, my last point here is that, okay, so this balance of forces, right? This occurs right at peak wind speed. But we know that the tornado has a life cycle. It doesn't drop out of the cloud as an EF5. It comes down kind of ropey-like, starts to build, and then decays. And so the amount of energy is where the wind is blowing the fastest, or that percent area is only a small fraction of the total damage area. So we can look at the intensity threshold by percent area. And now we can integrate our velocities over the damage path. And we can start to think about integrated kinetic energy, because this is a quantity that we can total up. We can sum up energy, total energy. And so that's what we do. We get this integrated kinetic energy over all the tornadoes since '94. This histogram, it's on a log scale, so it's a very nice distribution, very nice. And then we can look at it over time. Okay, so this is the annual integrated kinetic energy in gigajoules. Again, totaling, we have the total number of storms. Each storm has a kinetic energy, integrated kinetic energy, and I sum them up. And so this is the gigajoules per year for each of the tornadoes in the US. And you can see that there is a remarkable upward trend. So, you know, these findings really, to me, suggest a very new area of hazard research. How climate affects tornadoes and other severe local storms. It opens up a lot of questions. And I think we're starting to answer those questions. We're starting to get some answers. And these are the tools we're going to use. So what I'd like to do is to gather the scientists in the tornado field and some scientists in the climate field and get them together, sit down, and we're going to do that in Crete next spring, May 25th through the 30th. And maybe for the first time, get the scientists in these two fields talking to each other, and hopefully we'll make some progress. Okay, so I'll open it up to questions now. Thank you very much.
Hi, Stephanie Agburn, Climate Wire. This is interesting. I guess my first question is, what would the mechanism be that would connect increased tornado intensity with climate change?
That's a great question, and I really haven't thought that one through very carefully yet. I think it's, of course, the natural logical step, because I'm still not convinced these trends are real. That is, they're related to climate. If I was a betting man, I'd say I think they are, at least some of them. Some of the upward trend is related to climate. But I think there still could be some systematic changes in the way we've evaluated our damage paths over the years that could be contributing to the upward increase in trend in intensity. So since I think that at least part of it is due to climate change, I think the first thing we look at is greater moisture. So a storm can stay on the ground longer if it has a continuous feed of warm, moist air. And we see increases in humidity. We've seen increases in humidity at low levels across the plains where these storms form. And so I think that's the first culprit that I would look at, the increasing moisture at low levels.
Hi, Rich Monastersky with Nature. Can you pull up that slide again with the trend? It looks like that nothing happens from the 70s through 2000, and then you've got an upward trend. I mean, if you block out after 2000, is it completely flat?
Yeah, it's pretty flat, but it is going up. It's just not going up as rapidly as post 2000.
So do you have an explanation for that?
Again, I would not want to speculate on the changes in that slope, because I'm not even sure the slope itself is that completely real. So now you're adding another layer, which is the change in that slope, and I'd be very careful about trying to suggest that I can deconstruct that.
And have you binned the data at all by region?
I have. I haven't done this comprehensively, though, but the trends are most pronounced farther south. And so again, we might be able to answer some of these climate change questions by looking at it geographically, or at least getting some hints about it by doing those kind of regionalizations.
Rick Lovett, freelance. One of the other things that jumps out at me off that graph, although you have relatively few data points there, is a massive increase in variability at the end. Is there an explanation for that other than, I mean, that almost seems more dramatic than the upswing. You've got those two really high years followed by low ones.
Yeah, that's a great point. Again, we're integrating this, so we're summing up the energy. And so you can imagine that only a very few tornadoes contribute to most of the energy in a given season. And so it's possible that we're seeing fewer but stronger. So we can maybe see that kind of fluctuation in a climate that has fewer but stronger.
Any other questions?
Becky Oskin, Life Science. So thanks for going over in detail how you developed your model, but I wanted to ask you to do it again very briefly, as if you were talking to somebody who is a lay reader.
Okay.
And that's the audience that we're going for. So how would you explain it to somebody who has no background in science whatsoever?
Okay, I would say that the intensity of a tornado depends on how long it's on the ground to some extent. And so that relationship can be used to understand if the storms are they're staying on the ground longer, then we can assume that they are getting stronger. There's a relationship there that allows us to understand the intensity of a tornado through a characteristic of how long and wide its path is. And so these paths are they're going up by about 2 percentage points per year. And that translates to about 0.5 percentage point in velocity per year. Yeah.
So you mentioned the bias in measuring these paths around cities, populated areas. But can you describe how these paths are actually just measured in general, and if that's changed at all? So the boundaries, the outer boundaries, what's that like? How do people measure that?
Yeah, that's a great question. So how do we know, what kind of surveys and the changes in the survey methods? Well, these surveys are done a lot of time by the National Weather Service. They'll send out crews. But there'll also be, especially in the stronger tornadoes, there'll be independent experts that go out to look at the damage for insurance purposes. And so oftentimes you'll get a couple estimates of the damage. And so I don't know the details about how they do it, but they generally start to look where the most damage is and then move out from there. And so it's possible that with greater, maybe greater emphasis over time, that could lead to longer and wider paths, yes. I mean, we can imagine, though, that it's possible that there would be shorter paths, too. So any kind of systematic error is what we're worried about. I mean, we need to understand, but variability from one group to another really doesn't matter too much for this kind of model.
Other questions?
Liz Callagher from Environmental Research Web. What type of research collaborations would you be looking to have come out of your conference in May?
Well, first of all, I'd like to have just the folks who are experts on tornadoes and to start talking with the climate folks and trying to understand what are some of the ways we can address this question of what might be happening to tornadoes. And I think we need to have the tornado community and the climate community to agree on the data sets. I think there's a lot of folks who just have an opinion that the data are not reliable to do what you want to do, but I haven't seen any critique in a systematic way to show that that is in fact has occurred. And so we need to be able to have those kind of conversations about the data and why this might be occurring if in fact some of it's due to climate change.
Stephanie Agburn, Climate Wire. I was curious if you had gotten any feedback from the storm community about your metric for measuring tornado intensity, given that it seems like it's not one in wide use.
Yeah, well, I have. In peer review, I have gotten some comments, generally favorable comments. But remember, I'm doing this not as a way to estimate a future tornado intensity. Okay, this is not a model that's going to say, we can forget about Doppler on wheels. Okay, this is no way doing that. It's simply saying that historically we have length and width as our characteristic, and so we can try to assign some kind of intensity from that. I run into more headwind when I start to try to explain this trend from a climate point of view. Then the tornado folks really aren't that interested in discussing that part of the research.
Kit Stoltz, NCIA. You mentioned at the start a comparison with hurricanes. Some hurricane researchers see a relationship between ENSO and hurricane formation. Is there any speculation along those lines with tornadoes? Yes,
absolutely. I think there is there's some evidence that the El Nino or the ENSO phenomena could affect the frequency, especially the regional frequency, so more of a shift in where it's more likely to be active in a given year. But a lot of that research is really just beginning.
Do we have any other questions?
Hi, Boston Hunt, freelance. I'm still looking at this graph. I think a colleague just said it's flat until 2000, but if I keep looking, it's flat until 2008 or something. So my first question would be, how do you decide the band? How do you interpolate? And secondly, is there are there any models out there of how tornadoes work that would predict like a stepwise sudden increase in tornado strength when the atmosphere, for instance, exceeds a certain humidity or whatever?
Yeah, I mean, that's a great question. I think at this point in the research, I don't think I can answer that. I think it will take some more effort to understand again, the portion of that change that's real and a portion that's just due to systematic changes in efforts to survey these storms.
And the smoothing?
The smoothing is a local regression smoother, so I'm just using local points to fit a curve through that data, and those are the uncertainty bands on the local fit. So it's a nonlinear trend, if you will. It's again more for your eye than for a claim that things have changed.
Other questions? Any questions from the chat? Okay, then that's it for this press conference. Thank you, Dr. Elsner, for your presentation, and thank you, everyone, for being here. And our next press conference will be tomorrow morning at 9 a.m., the weak solar cycle and its consequences. We hope you'll be here.